Welcome back. In this segment, I want to emphasize again the strong connections between induction and recursion. Now, it turns out when you're studying the properties of an object or an entity that's defined recursively, it is often very natural to write a proof by induction. So in this short segment, I want to illustrate this fact by using one of the functions that we discussed earlier in the lecture, namely the function f of m comma n, which is defined as 1 if n is equal to 0, and as f of m and n minus 1 times m otherwise. Remember that I asked you to figure out what function that was. So the answer is that f of m comma n is the exponential function. More precisely, m is the base of the exponential and n is the exponent. So now what I want to do is prove that fact, which I'm going to state as a theorem. For all m and n, where m and n are non-negative integers, f of m comma n is equal to m to the power n. So let's write a proof by induction of theorem 2. I can tell we're going to write a proof by induction as opposed to a proof by strong induction because the value of f for a particular n is defined directly by the value of f for the previous n. We don't need to go any further back, so we don't need a strong hypothesis here, just the basic hypothesis of mathematical induction. Now notice you may not have realized why it was important before when I said prove by induction on n, to specify the variable on which the induction operates. Well, here it's crucial because there are two variables in the function definition. And notice every case, the base case and the recursive case, are defined in terms of n. So the recursion operates on n, not on m. That's why it's important to state that the proof is by induction on n, especially in this case. Now, let's start the proof with the basis step. The basis step is to prove p of 0. So what is f of m and 0? By definition, that's equal to 1. And what is m to the power 0? Well, by definition of the exponential function, that's also equal to 1. And therefore, f of m comma 0 is equal to m power 0, which establishes that p of 0 holds. Now, let's turn our attention to the inductive step. Remember that we need to make a hypothesis called the inductive hypothesis. And here the hypothesis is that f of m comma n is equal to m to the power n for an arbitrary non-negative integer n. And then we're going to establish p of n plus 1, which is we're going to compute f of m comma n plus 1, and we want to prove that that's equal to m to the power n plus 1. Now the first step in rewriting this term is to use the definition of f. Since the second argument here, n plus 1, is known to be greater than 0, we're going to use this case in the definition of f. We're going to plug in n plus 1 for n, and what we're going to get is f of m comma n times m. That's just the definition of f. Now we can replace this term by m to the power n. And that's according to the inductive hypothesis. And finally, we can just apply the law of exponents to get m power n plus 1, which is exactly what we need to prove p of n plus 1. So this concludes our proof of the inductive step, which, together with the basis step, proves theorem 2. Now this is a pretty simple property of that function f, but the point of this segment again was to make it very clear that there's a strong connection between induction and recursion. And in particular, when you study the properties of recursive objects, it's very natural to end up writing proofs by induction.